Hello sir, today I will be demoing my project, Support Vector Machines for Heart Risk Classification. So the goal of this is to classify individuals as either high or low risk for heart-related conditions using machine learning. So here we utilize SVM, a powerful classification algorithm, and we compare three different SVM models, linear, radial basis function, and polynomial kernels to see which one best predicts heart risk. And we evaluate their performance using key metrics like accuracy, precision, and recall. So first we start with data pre-processing. So in here, this is where we set up our data for modeling. First, we import our necessary libraries like pandas, which help us work with our data tables, and standard scaler, which is crucial for preparing our features. And then we use the code df equals pd.read.csv to load our heart attack risk dataset from a CSV file into a pandas data frame. And then we show the output using dfhead, and a quick look at the first few rows gives us a glimpse of our data. And you can also see that our columns like age, cholesterol, blood pressure, and our target heart attack risk. And then using this code, df is null sum, we can see that thankfully our dataset is clean and it has no missing entries. And then we move into separating features and targets. So we separate our input features, which is the large X, from our target variable, the small y, which is heart attack risk. And this y column is what we want our models to predict. And then we move into scaling features for the SVM. So finally, we scale our features because SVMs are sensitive to the scale of input features. So standard scaler transforms our data to have a mean of 0 and unit variance. This prevents features with larger values for dominating the learning process. Now we move into part B, where we train our SVM models. So we first import SVC, our core SVM classifier, and the metrics we'll use for evaluation later are accuracy score, precision score, and recall score. So we first train the linear kernel SVM. So in this code, we start by training the SVM, and this model attempts to find a straight line or a hyperplane to separate the classes, and we fit it to our scale data. And then we train our RBF kernel SVM, and the radial basis function kernel is excellent for capturing nonlinear patterns in the data, which creates more flexible decision boundaries. And then finally, we train the polynomial kernel SVM with a degree of 3, and this kernel allows for curved decision boundaries which can fit more complex relationships. Now, after training, we use each of our models to make predictions on our scale dataset. And to get a quick sense of their performance, I created this comparison table showing the first 10 actual values against the predictions from each of our SVM models. Now we move to the next major part, which is evaluating the SVM models. So this is where we see how well each model truly performed. So first we evaluate the linear kernel, and for the linear SVM we see an accuracy of about 90.9%, its precision is 74.2%, and recall is 62.1%. While accurate is generally, its lower precision means it made more false positive errors, and its recall indicates it missed a significant number of actual high-risk individuals. Now for evaluating the RBF SVM, shows a slight improvement in accuracy to 91.9% and a better precision of 81%. However, its recall remains similar, suggesting it still struggles to identify all true high-risk cases. And finally, for evaluating our polynomial SVM, it shows that it performed the best because it achieved the highest accuracy at 92.6% and an impressive precision of 85.6%. So this means that when it predicts someone is high risk, it's very likely to be correct. Recall, however, stayed consistent with the other models. So for the summary, the polynomial SVM was the strongest performer, especially in precision, while all models showed high overall accuracy. And the consistent recall of around 62% across all models suggests that there is still room for improvement in our ability to catch all actual high-risk cases. And then we move to our next major part, which is to visualize the SVM decision boundaries. So here we visualize these boundaries. Since we can't easily visualize in many dimensions, we pick only two key features, which are age and cholesterol. And you can see it in this code. Yes. Okay lang. Okay. So just like in our full dataset, we scale these two features. And now we plot it using this function first. I built this function to easily create the plot for each of the SVMs. So now here we are for the decision boundaries of our SVMs, and here they are. So as we can see, for the linear SVM, there is a mostly vertical straight line, heavily relying on age, and then there is a significant overlap of red, high risk, and low risk points across the boundary, which indicates many false positives and false negatives. So the data is not linearly separable by these two features. Then for RBF SVM, there appears to be very similar to the linear SVM, where there is mostly a vertical line, but the RBF kernel doesn't find significantly non-linear separation here. And there's also high overlap, which persists, and many misclassifications. So visually, there's no noticeable improvement over the linear model. Then for the polynomial SVM, again, there's strikingly similar linear and RBF plots with the vertical separation. And despite its potential for curves, it acts linearly here. So it still shows substantial overlap across and misclassifications. So all three SVM kernels exhibit very similar, nearly linear decision boundaries when only considering age and cholesterol. And the plots clearly show that these two features alone are insufficient to cleanly separate high-risk and low-risk individuals. So for our final evaluation and reflection, to recap our model performance summary, the polynomial SVM achieved the highest overall performance with strong accuracy and precision. And then our analysis of precision is especially important in this health risk scenario, as we want to avoid incorrectly labeling someone as high risk. While precision was strong, the consistent recall of around 62% across all models shows we still have room to improve in identifying all actual high risk cases. So this project showed us that even sophisticated models like SVMs can behave linearly if the data suggests it. To further enhance our model, especially to boost recall, we could explore feature engineering, adding more health or lifestyle indicators, fine-tune our hyperparameters, or even experiment with entirely different machine learning models like decision trees or ensemble methods. So for our conclusion, we hope this we hope this demo has provided clear insight into our SVM Hartress classification project. So it shows the importance of model selection, thorough evaluation, and data quality in building reliable predictive tools, especially in critical applications like healthcare. So thank you for watching, sir. That's all.